Welcome to our deep dive into the world of supersymmetry, or SUSY, as I'm sure you all know it. We've got some fascinating research papers and some really interesting expert opinions to unpack. This theory, it's been called, well, some call it the grand unified theory of everything.
Yeah, that's right. It really tries to bridge the gap between, the two fundamental types of particles we have, fermions and bosons, and suggests this kind of unique symmetry between them.
And I know that you guys know all about fermions and bosons, but for anyone who needs just a quick refresher, fermions are really the building blocks of matter. So, things like electrons and quarks, and then bosons are what carry forces, like photons. They're responsible for light. And SUSY basically proposes that every single fermion has this boson counterpart and vice versa.
Exactly. And these theoretical counterparts that we're talking about, they're called superpartners. So, if you take an electron, which is a fermion, it would have a selectron superpartner,
Yeah.
and that would be a boson, and so on. And, it sounds kind of simple, but this has some really profound implications for how we understand physics.
Yeah, it's not just about finding these neat little pairs, right? I mean, SUSY aims to resolve some of the biggest, well, I guess you could say mysteries in physics. One of the papers that you sent in actually focused on this. It's called the hierarchy problem. And this is the perplexing weakness of gravity compared to other fundamental forces. I mean, it's crazy to think that something as small as a fridge magnet can actually defy like the entire gravitational pull of the Earth.
Yeah, and it really, highlights this vast difference in strength between gravity and say, electromagnetism. SUSY offers up an explanation for this by suggesting that the strengths of these forces actually change with energy scales. It's kind of like we're adding new players to the game. These super partners, they're influencing the rules, but at different levels of energy.
So the super partners, they're influencing the game behind the scenes, and we just see their effects sort of indirectly through the forces that we observe.
Exactly. And the equations that are in the standard model, which is our current best description of particle physics, they require these really precise adjustments to explain the mass of particles and also the strengths of forces. This fine-tuning problem, as it's often called, makes a lot of physicists kind of uncomfortable because it seems unnatural. But SUSY, with its introduction of superpartners, it could offer a much more, I guess, elegant and natural explanation for this observed mass hierarchy.
Instead of a universe sort of precariously balanced, on a knife's edge, we get a more stable and inherently consistent system. It's fascinating. One of the papers even dove into how specific calculations within SUSY models, particularly the cancellation of certain loop diagrams, could actually provide this stability.
Yeah, it's pretty intricate, but essentially these loop diagrams, they represent quantum fluctuations that contribute to the masses of particles. But when you introduce superpartners, their contributions to these loops, they actually cancel out those problematic terms. And that leads to a much more stable calculation.
So it's not just adding these new particles for the sake of symmetry. It's introducing this whole mechanism that actually addresses a really fundamental problem in how we understand particle masses. Now let's move beyond the standard model a little bit. A couple of the sources that you shared, they delve into something called the minimal supersymmetric standard model, or MSSM. Can you unpack that for us?
Sure. The MSSM is basically, it's the simplest supersymmetric extension of the standard model. So it takes all the known particles and forces, and it just adds in superpartners.
And this leads to some really interesting predictions, right? What are some key takeaways from these MSSM papers?
Well, the MSSM, it makes some specific predictions about the properties of superpartners, including their masses and their interactions.
Yeah.
So, for example, it suggests that the lightest superpartner should be stable and also electrically neutral, making it a prime candidate for dark matter.
Dark matter. This is, the universe is invisible matter that we only even know exists because of its gravitational effects. So SUSY could actually potentially solve two massive mysteries with one elegant framework.
Yeah, it's a very compelling possibility. And one of the papers you sent even explores how a specific superpartner that's predicted by the MSSM, called a neutralino, fits the bill for dark matter remarkably well. Its properties, they actually align with what we observe in terms of, how dark matter gravitationally influences galaxies and galaxy clusters.
That's incredibly exciting, but we can't just sort of take these theoretical predictions at face value, right? We need experimental evidence. And several sources that you send in, they focused on the hunt for these superpartners, particularly at the Large Hadron Collider.
Yeah, the LHC, it's our most powerful tool when it comes to probing the fundamental nature of matter. And scientists, they're smashing protons together at these incredible energies, and they're hoping to catch, maybe a glimpse of these elusive superpartners.
It's like a cosmic detective story, with the LHC serving as our magnifying glass. But so far, the super partners have, well, they've remained elusive. How are physicists interpreting these results?
Well, even though we haven't found any direct evidence of superpartners, these experiments haven't actually ruled CUIs out completely. Each search that happens at the LHC, it places constraints on the possible masses and interaction strengths of superpartners. So we're narrowing down the search space for theorists.
So each null result is it's guiding future searches, and it's refining our understanding of where these super partners might be hiding. What are the chances of finding them in future LHC experiments?
Well, the LHC is actually undergoing some upgrades right now to increase its energy and luminosity. So, more collisions at higher energies. And these upgrades could really increase the chances of creating and actually detecting these superpartners, particularly if they're within the energy range, that's accessible by this upgraded LHC.
Yeah, it's like we're upgrading our detectives toolkit, giving them a better chance of actually finding these elusive clues. But SOSY's implications, they don't just end with particle physics, do they? I mean, several of the sources that you shared, they dive into its connection with string theory.
String theory. It's this mind-bending idea that the universe is made up of these tiny vibrating strings, and it attempts to, unify all forces and particles in the universe.
Hmm.
And so SY actually plays a really crucial role in its consistency.
Okay, this is where things are really mind-blowing. Tell us more about this cosmic connection.
Well, string theory in its purest form, it actually suffers from some mathematical inconsistencies. It leads to, nonsensical results. But remarkably, when you incorporate SOSY into string theory, it helps to resolve those inconsistencies.
So SOSY is like this missing piece of the puzzle. That makes string theory more mathematically elegant and consistent.
You could say that. CSY really helps to tame the mathematical chaos, of string theory. And it makes it a much more viable framework for understanding the universe at this really fundamental level.
And I understand that CUSY's influence actually extends even further into, the realm of extra dimensions that string theory proposes.
Oh, absolutely. String theory requires these extra spatial dimensions,
Yeah.
beyond the three that we experience. And CSY, it helps to manage these extra dimensions. It ensures that they behave in a way that actually makes sense, mathematically.
This is all incredibly fascinating. So
Yeah.
so CUSY helps string theory make sense. It tames these extra dimensions, and it brings us closer to a unified understanding of the universe. That's quite a resume.
Yeah, it's a powerful and elegant framework
Mm.
with implications that really span, from the subatomic realm all the way to the vast expanse of the cosmos.
I mean, it's mind-boggling to think that these tiny, hypothetical super partners, they could actually hold the key to understanding some of the universe's biggest mysteries. But before we, get ahead of ourselves, we need to acknowledge that despite its allure, SUSY does face some challenges.
Oh, of course. As with any scientific theory, we have to critically examine its shortcomings and address the open questions that it raises.
That's what makes the scientific process so compelling, right? This constant back and forth between theory and experiment, pushing us to refine our understanding of the universe.
Exactly. And in the next part of our deep dive, we're actually going to delve into some of these challenges, and we'll also explore some alternative theoretical frameworks that have emerged alongside SUSY.
Welcome back. So we left off talking about, SUSY's potential to really revolutionize our understanding of the universe. But, as with any scientific theory, it's not without its critics.
That's right. As compelling as USY is, we have to address some of the challenges and some alternative perspectives that have come up.
And one of the biggest hurdles that faces USY is this lack of direct experimental evidence. Despite decades of searching and using increasingly powerful colliders, those elusive superpartners, they remain stubbornly hidden.
Yeah, indeed.
Mhm.
And the lack of any definitive, signs of superpartners at the LHC, it's led some physicists to, propose these alternative theories,
Mhm.
while others are, continuing to refine CSY models to try and and better match the experimental constraints that we have.
So it's a bit of a fork in the road, with some physicists sort of venturing down these new theoretical paths, while others are remaining committed to CUSY, and adapting it to fit the latest experimental findings. Can you give us a sort of overview of some of these leading alternative frameworks?
Sure. One prominent contender is something called Technicolor, and it's a theory that proposes that the Higgs boson, this particle that we think is responsible for giving other particles mass, it isn't actually a fundamental particle, but it's actually a composite particle. It's made up of even smaller, more fundamental particles.
So it's kind of like saying the atom isn't the smallest building block, but rather there's a whole like subatomic world that we haven't even explored yet.
Yeah, that's a good analogy. And just like SUSY, Technicolor predicts, new particles that could potentially be discovered in future collider experiments.
It seems like the search for new particles is a common theme in a lot of these theories. Are there any alternatives that don't rely on adding these new particles to the mix?
Yeah, there are. Another alternative is something called modified gravity. And it proposes that maybe we don't need, new particles to explain these mysteries of the universe, but rather a refinement of how we understand gravity itself.
So instead of adding new ingredients to the cosmic recipe, we're kind of tweaking the instructions.
Exactly. And these theories, they suggest that maybe our current understanding of gravity, as described by Einstein's general relativity, it needs some modification at very high energies or very large distances.
It's fascinating to consider that even Einstein's groundbreaking theory might not be the complete picture. Does modified gravity offer any testable predictions that could actually differentiate it from CUSY?
Yeah, modified gravity theories, they often predict these subtle deviations from general relativity's predictions. So, things like slight variations in the gravitational force at very large distances. And these deviations, they could potentially be observed in the motions of stars and galaxies, or even in the behavior of light bending around massive objects.
So astronomers and cosmologists they're essentially playing detective as well. They're searching for these clues in this vast cosmic tapestry that could point towards modified gravity or other alternative theories.
Exactly. The universe is a vast laboratory.
Yeah.
And we're constantly searching for new ways to test our theories and refine our understanding of its fundamental laws.
It's a testament to the ingenuity and the persistence of scientists that we we continue to push these boundaries of knowledge even when faced with these profound mysteries. But let's not forget SUSY just yet. One of the sources that you shared actually dives a little bit deeper into this concept of SUSY breaking, and this could actually be a key to reconciling the theory with the lack of observed superpartners.
Yeah, that's a crucial point. For SUSY to be a realistic description of the universe, supersymmetry has to be broken at some energy scale. So that means superpartners wouldn't, have the exact same mass as their standard model counterparts. And this breaking mechanism, it could explain why we haven't seen, superpartners yet. If they're much heavier than their partners, they would require these much higher energies to produce, which could be, beyond the reach of our current colliders.
So SUSY breaking it's essentially a way to hide the superpartners,
Yeah.
making them harder to find.
In a way, yeah. It's like saying superpartners are playing this cosmic game of hide and seek.
Yeah.
And the breaking mechanism kind of determines, how well they're hidden.
But there must be some rules to this game, right? I mean, aren't there different scenarios for how CCY breaking could occur?
There are. And different SUSY breaking scenarios predict different patterns for the masses and interactions of superpartners. So for example, some models suggest that CSY might be broken at very high energies, which would make superpartners extremely heavy and very difficult to detect. Others, they propose that the breaking occurs at lower energies, which could potentially be within reach of future experiments. So the hunt for these superpartners, it's intertwined with this search for the specific mechanism of SUSY breaking. It's like searching for a hidden treasure, but with a map that's partially obscured. A very, very apt analogy. And understanding this mechanism of SUSY breaking, it's not just important for finding superpartners, but it's also important for understanding its implications for cosmology and the evolution of the universe.
That brings us to another really intriguing aspect of SUSY that we haven't really explored yet, and that's its potential to explain the origin of dark matter and this asymmetry between matter and antimatter in the universe.
Exactly. As we touched upon earlier, some CSY models predict that certain superpartners, like the neutralino, could actually be excellent candidates for dark matter. Their properties, they align really well with what we observe in terms of dark matter's gravitational influence
Yeah.
on galaxies and galaxy clusters.
So if these super partners do exist and they are indeed dark matter, then CUSY would have played this really crucial role in shaping the large scale structure of the universe.
Exactly. These invisible superpartners, they would have been pulling the gravitational strings behind the scenes
Yeah.
and influencing how galaxies and clusters of galaxies formed over billions of years.
It's like this cosmic dance, with dark matter leading the way, guiding the formation of the structures that we observe today. But what about this matter antimatter asymmetry?
Yeah, that's another, really profound mystery. We know that the universe is predominantly made of matter, but in the Big Bang, matter and antimatter, they should have been created in equal amounts. Where did all the antimatter go?
It's one of the biggest unanswered questions in cosmology. Does SUSY offer any insights into this puzzle?
Well, some CSAY theories propose that specific interactions, involving superpartners, could have generated this slight excess of matter over antimatter in the very early universe. And as the universe expanded and cooled, most of the matter and antimatter it annihilated,
Yeah.
leaving behind this small surplus of matter that makes up, the universe that we see today.
So USY could potentially explain why we even exist.
It's a captivating possibility. If CUY is the correct description of nature, it would mean that these hypothetical superpartners, they played this vital role in the universe's evolution from the first moments after the Big Bang to the formation of galaxies and even the very existence of matter itself.
That's quite a legacy for particles we haven't even, discovered yet.
It's a testament to the power of theoretical physics,
Mm.
to explore these most fundamental questions about the universe's origins and really the nature of reality.
This deep dive has been truly illuminating, revealing the multifaceted nature of SUSY and its potential to answer some of the universe's deepest mysteries. But we'd be remiss if we didn't acknowledge some of the criticisms and the concerns that have been raised regarding SUSY.
Of course, it's important to engage with these criticisms and consider these alternative perspectives as we continue our quest to understand the universe.
And one of the most common critiques of SUSY actually revolves around this issue of fine tuning. This idea that some SUSY models require these very precise adjustments of parameters to match what we observe in nature.
And this fine-tuning, it's a valid concern. Some physicists, they argue that the degree of fine-tuning that's required in certain CSY models, it's unnatural and it points towards a potential flaw in the theory.
So it's like saying the universe is balanced on a knife's edge, and any slight deviation from those finely tuned parameters would kind of throw everything off kilter.
That's one way to think about it. And it's a valid point that theorists are actively, addressing. They're proposing these new models and mechanisms to try to explain this apparent fine-tuning or mitigate its implications.
Are there any specific examples of how theorists are kind of tackling this issue?
Absolutely. One approach is to explore these new mechanisms for SOIS-Y, breaking that naturally lead to the observed mass hierarchy, without requiring this excessive fine-tuning. Another avenue is to consider extensions of the MSSM,
Yeah.
that introduce these new symmetries or particles that could address the fine-tuning problem.
So it's a dynamic field with theorists constantly, refining their models and exploring new possibilities in response to experimental constraints and theoretical challenges.
Exactly. It's this ongoing conversation between theory and experiment,
Yeah.
pushing us to refine our understanding of the universe and to explore, new frontiers of knowledge.
And that's what makes science so fascinating. It's a never-ending quest for answers driven by curiosity and a willingness to challenge our assumptions.
It's a journey we're all on together,
Yeah.
constantly seeking this deeper understanding of the universe and our place within it.
Well said. This deep dive into SUSY has been an incredible journey, exploring its potential to revolutionize our understanding of particle physics, cosmology, and really the very nature of reality. But before we wrap things up, we want to address one more crucial question. We've explored the intricacies of CUSY, its strengths, its challenges, and even its potential rivals. But one question sort of kind of lingers.
Yeah.
If SUSY is actually confirmed, I mean, what would it mean for our understanding of the universe?
That's a question that's really captivated physicists for decades.
Yeah.
Confirmed CUSY, it would be monumental.
Yeah.
It would reshape our whole understanding of particle physics and the cosmos. It would mean, a whole new family of particles exist, influencing the universe in ways we're only just beginning to grasp.
I mean, it'd be like discovering this hidden continent, teeming with new life and resources we never even knew existed. What are some of the most profound implications you foresee?
Well, for starters, confirmed CUSY would provide this really strong support for string theory, potentially even bolstering its claim as the theory of everything.
Hmm.
CUSY's role in stabilizing string theory and managing these extra dimensions, it would become more than just, theoretical elegance. It would be this validated feature of reality.
So string theory, which is often criticized for being too abstract and untestable, would suddenly have a much firmer footing in the realm of observable physics.
Exactly. And the implications they extend, beyond string theory. Confirmed CSY could actually give us a much deeper understanding of dark matter, potentially resolving one of the biggest mysteries in cosmology. Imagine being able to pinpoint the exact nature of dark matter. This substance that makes up the vast majority of matter in the universe, but it remains invisible to us.
It would be a total paradigm shift, allowing us to map the universe's structure with this unprecedented detail, and potentially even harness dark matter's properties for technological advancements.
The possibilities are really truly mind-boggling, and let's not forget about the potential for understanding the matter-antimatter asymmetry. CSY offers these mechanisms that could explain why the universe is dominated by matter, which is a prerequisite for our very existence.
It's a humbling thought that these hypothetical super partners, if they exist, they may hold the key to understanding, why we are even here at all.
Yeah, it highlights the interconnectedness of the universe. How these seemingly abstract concepts in particle physics can have these profound implications for the grandest cosmic scales.
This deep dive has been an incredible journey, exploring this world of hidden symmetries, elusive particles, and really mind-bending possibilities. Even if SUSY is never directly confirmed, its influence on theoretical physics and our quest to understand the universe, it's undeniable.
It's really pushed us to ask, these bolder questions, develop new mathematical tools, and explore these uncharted territories in this vast landscape of physics.
Whether SUSY is the ultimate answer or just a stepping stone on the path to an even deeper theory, it's really enriched our understanding of the universe, and it's inspired a generation of scientists to continue probing the mysteries of nature.
It's a testament to the power of human curiosity, our drive to unravel the secrets of the cosmos and our relentless pursuit of knowledge.
We hope this deep dive has sparked your own, curiosity about the fundamental nature of reality and the incredible potential of theoretical physics.
Yeah, keep exploring, keep questioning, and keep looking up at the stars with wonder. Who knows what other mysteries the universe holds, just waiting to be discovered.